Welcome to 5-Minute BTech channel. Today, we're going to pull back the curtain on your computer's operating system to uncover the secret life of a program.
Okay, so think about it. You see an icon, you double-click it, and boom, your application just appears. It feels like magic, right? But what's really happening in that split second? Well, it's not magic, but it is a fascinating journey from a lifeless file on your disk to a dynamic, living thing that your OS has to manage. So let's dive in. All right, first things first, we need to get to know the main character in our story, the process. It's a word you've probably heard 1,000 times, but believe me, it's so much more than just the code for an app. At its heart, the definition is actually super simple. A process is just a program that's actively running. So that static icon you clicked, that's the program. The window that's open and doing stuff on your screen right now, that's the process. Simple as that. But a process is way more than just lines of code. You got to think of it like a complete package. It's got the data it's currently working with, all the resources it's borrowing from the system, like CPU time and memory, and super importantly, its current execution state. It's a whole self-contained little universe for your program to live in.
So with maybe hundreds of these processes all running at once, how on earth does the operating system keep track of everything? Well, it gives each and every one an identity card, kind of like a passport. This is called the Process Control Block, or PCB for short.
And this isn't just some simple ID card. The PCB is the OS's single source of truth for every single thing about that process. If the OS is a busy manager, then the PCB is the super detailed personnel file for each employee.
So what's actually inside this thing? It's packed. You've got a unique process ID, or PID. It's got the current process state, is it running, is it waiting? It's got the program counter, which is like a bookmark telling the CPU exactly which line of code to run next. Plus, it holds CPU register values, memory details, a list of any open files, and even scheduling info like its priority. Literally, every single detail the OS needs is right here.
And here's the takeaway. This is absolutely crucial. The PCB is everything. If a process gets paused for even a microsecond, the OS saves its entire life into the PCB. Without it, the OS would have no clue how to restart that process exactly where it left off. It would be totally lost.
Okay, now let's talk about the life cycle of a process. A process isn't just on or off. It actually moves through several different stages, or states, during its lifetime. It's pretty interesting.
This is the classic 5-state model. First, it's new while the OS is getting everything set up. Then it moves to ready, which means it's sitting in a line waiting for its turn on the CPU. When the scheduler finally picks it, it goes into the running state. Now, if it needs to wait for something, say a file to download, it becomes blocked. And finally, once its job is all done, it enters the terminated state. This whole idea brings us to the real magic trick that makes multitasking possible: context switching. I mean, how can one CPU core run your web browser, your music player, and everything else all at the same time? Well, spoiler alert, it doesn't. It just switches between them so incredibly fast that it looks like it does. It's like a master juggler with dozens of balls in the air. So let's picture this. We've got process A, and it's currently running on the CPU. At the same time, process B is in the ready state, just patiently waiting for its turn. The OS decides it's time to give process B a shot. The very first thing the OS does is hit the pause button on process A. It takes a complete snapshot of its current state, the program counter, CPU registers, all of it, and saves everything safely into process A's PCB.
And then, in the very next moment, the OS grabs the PCB for process B. It loads all of that process's saved information back onto the CPU. Just like that, process B can pick up running exactly where it left off as if nothing ever happened. That entire swap? That's a context switch.
But there's always a catch, isn't there? While the OS is busy saving and loading all this stuff, no actual work for your applications is getting done. This is called overhead. Ever wonder why your computer starts to stutter when you have 50 tabs and a game running? It's partly because the CPU is spending so much time just switching between tasks. That's the performance price we pay for multitasking. So where do all these processes hang out when they're not running? They don't just float around randomly? The OS is a great organizer. It puts them into neat little lines, or as we call them, queues. And there are different queues for different things. The job queue is like the master list of every single process in the system. The ready queue, which we've talked about, is specifically for processes that are ready to go and just need the CPU. And if a process is waiting for, say, your hard drive or the network, it gets put into a specific device queue.
This organization is absolutely key to keeping things running smoothly. So there you have it, from a simple icon to a living process, managed by a PCB, moving through states, and juggled by the CPU. That's the secret life of a program. But this whole symphony of processes needs someone to decide who gets to play next, which brings up our final question. If the OS is the conductor, what part actually makes that decision? Well, that's the supercritical role of the scheduler. But that's a story for another time.
If you liked the video, hit like and subscribe the channel, and I'll meet you in the next video.